Okay, let's continue. So we are constructing the universe of ordinary mathematics, and now we reach the language. So language L. In this language we use some symbols. So these symbols, let me remind you, are divided in three groups. The first group contains the symbols equal, element of, not, and there exists, brackets, restriction, and comma. There exist other symbols, of course, like this, but they are derived from this, as I will show soon. The second group, variables. Just a countable set of symbols which we like, any letters with indices and with decorations and so on. So variables. We need just countable number of them because the formulas and expressions are finite, and we can have not more than countable set of these objects, so we don't need more than countable number of variables for the language. And third, there are constants. It is more serious. Constants are not individual names of different elements of our superstructure. So we have a superstructure S is union Si. We have countable number of levels, and for each of these elements of each element of this superstructure, we assign some specific names. So here you have to distinguish between the names of objects and of objects themselves. And to do it when it is necessary, I will use the following notation. If we have object, say, A, element of S, it is element of S, or a set of sets, and so on. The name of A is like this. And the same with other things, so that we can distinguish between the names and the objects. Now, what can we do with this? So we define, first of all, the first sort of expressions or combinations of symbols. So expression is any finite sequence of symbols. Yeah. So it can be, say, all commas or any other. So mostly they have no meaning. So to have, to be able to have a meaningful things, we have to follow some rules. So first you define the object's named terms. So what is a term? say mu is a term, it is some expression, and we have the following thing. The first sort of term, mu, is some variable. Here I introduce this notation, which is borrowed, I think, from computer languages. The equality may have very different meanings, many different uses. Yes? So we can say that A equal B as a statement, just neutral statement. We say that these two things are equal. Or we can say, let us define A equal B. Yeah? So this is our definition. So when you write in this second sense, then strictly speaking, you have to use different notation. Yes, and this is different notation. So mu is, by our definition, a variable, any variable. Yeah. A second sort of terms, which is mu is a constant. So it is a constant denoting any element of our superstructure X. Then the third sort, suppose that you have two terms, mu and nu are terms. Then we can form another term, chi equals mu nu. It is ordered pair of terms is a term. And form, so if and nu are terms, then lambda equals mu restricted on nu is a term. We have defined what is mu restricted by onto nu. If mu is, say, relation, nu, for example, a function, and nu is some element of our universe. So if mu happens to be in the domain of mu, then we can define the value of this function mu on element nu. Yes? Otherwise, if they are not related in this way, it is empty set. Nothing. Yeah? So, so this is how we can combine terms. Now we can take these new terms, which were derived from the previous defined elementary terms, and again combine them using these operations, yes, as long as we need. So we can have, in fact, very long terms. Yes, here, say, mu is some crazy operation. Yes, like say solution of differential equation. Yes, nu is, say, the set of initial and boundary conditions. Yes, and mu restricted to nu is solution of this boundary value problem, for example. Yeah. So it is can be anything, and we can also substitute this into some other term, and we want to find, say, asymptotic behavioral solution of differential equation. So that new term will include some function which, say, takes some function and puts in correspond to this function its asymptotic behavior, say, at infinity. So this is the way how we proceed with this. So what I would say that grammatically terms are correspond to nouns. Yes, they have no qualities, there is no action, so it is just nouns, names of some objects. So either each term has the, after all, has the meaning of some element of our universe S cap. Either it is this element or it is nothing, but if it is nothing, it is empty set, which is also element of our universe. So terms are nouns. The next construction of our mathematical language is formulas. Suppose we have terms already. Mu and mu are terms as they were defined before. Now, suppose we already have some formulas, say alpha, beta, gamma, and so on, formulas. Then we can construct further formulas from this. So the formulas can have the following form. Formula alpha has the following form. Mu equals mu. Yeah? So unlike previous, this has this equality. So what if I say mu is equal to nu, it is already a grammatical sentence. It has both nouns and a verb. Yes? So next. Formula can have the following form. Mu is element of mu. Yeah. Now the next sort. Alpha is negation of beta, not beta. It is read alpha is not beta. Yeah. The next, alpha is beta and gamma. So it is, I would say, conjunction of two other formulas. Alpha has the following form. For there exists x in mu. What is mu? Mu it is a term. Which does not contain x, yeah? Such that beta so no, it is how to read it, but when we will discuss the semantics, semantics is the set of rules how to give some meaning to this formula. For now, these formulas are just collections of symbols, nothing more. They are purely formal, and their meaning depends on many other circumstances. Yes. In this connection, I recall one discussion which I had with the technical editor of Communications of Pure and Applied Mathematics. I submitted a paper to this journal, and in this paper, there were some formulas. Some of them were printed as a separate strings, and the formulas have, say, something equals something, as usual, and after this formula, I put either comma if the sentence was going further, or period if it was the end of the sentence, because I thought that in the formula we have a verb, this equality sign, we have nouns, what is before, to the left of the equality and to the right equality. So grammatically it is a sentence, or maybe a part of a sentence. So we have to deal with it as with a sentence and put either comma, or maybe semicolon or colon, as if it were a real sentence in our language. The technical editor said that the policy of his journal is that formula is a separate object and does not require any grammatical symbol after it. No comma, no colon, and so on. And so I asked why it is so natural, and say that in other journal I saw this usage. And he said that please, here is quotation from one textbook, here is quotation from other textbook about advanced English grammar. So, and asked, are you going to discuss it further? I said, no, I trust you completely. So the formulas were printed without these symbols after them. But in fact, in this text, I also don't use any symbols while I'm teaching to write them. But let us better not to do it. Now you see that this definition is recursive. Here the formula is defined and using some other formula. So this beta is also one of these 5 types of formulas, but it can also contain further formulas and so on. And we assume that after finite number of steps we get to elementary formulas like 1 or 2, and this is all. Okay, no example of formulas. Formulas. X element of y and x is not equal y. No. Not x equal y. For example, I don't ask if this formula has any meaning or if it is in any sense correct. Or for example, x element of A and y element of B, and there exists C such that x element of C and y element of C. No, again, this is, I would say, well-formed formula. So grammatically it is perfect. Its meaning can be different or can be absent at all. Yeah. In fact, every such formula has some meaning. We will look at it further. Now, in this formula, okay, I don't need it. As I said, formula can contain terms, and terms contain constants and variables. Yeah. There exist x in mu, if you consider this formula such that you have some formula alpha. Yes, formula alpha can contain x. Yes, and cannot contain x. It can happen this or that way. Suppose it contains x. Now, if we replace x by y different symbol in, say, it is a formula beta, in the formula beta, including all the instances of x in alpha, then the meaning of the formula does not change. No, let me example. Beta is the following formula. There exists x in mu, mu is a term, such that, say, x is an element of, say, some a. Now, if you replace x by y, you have beta prime. There exists y is in mu, such that y in a. A is an object, is element of our S. Now, clearly, these two formulas have the same meaning. Now, I'm going a little bit ahead of of what I'm going to explain, because the meaning is discussed further. But clearly, in the common sense, these two formulas say the same. In fact, y or x is immaterial. It is similar to what is written in analysis, say integral from a to b fx dx, or if you write integral from a to b ft dt, certainly they mean absolutely the same. So this operation of integration eliminates the specificity of this x. So x or p mute variable. Yeah. So this variable, its notation is not important. So therefore, in the formal language, you say that x is a bound variable. Yeah? X is a bound variable. On the other hand, the formula x is element of A. This x is not bound, because here is no sign, no quantifier there exists. Yeah. So this x is not signed. So in this case, x is a free variable. In general, every formula contains both bound variables and free variables. No, in the limit case, it contains no variables. Say the formula 1 minus 1 equals 0. This is a formula. It is shortcut for applying operation minus to 1 and 1. Yes? Let me write it. Minus 1, 1 is 0. So this is object minus. What is minus? Minus is a subset in the product, the Cartesian product R by R. So in R by R, so in the set of pairs x, y, there is a set x, y, say z. There is a set z equal x minus y. Yes, this set x, y, and z equal x minus y is a subset which is called minus. Yes, by definition, minus restricted on 1, 1. It is an element such that 1, 1, and this element is element of our subset, which is called minus. Yes, and so we have there is a term. Yes, because we have 1. 1 is a constant. We have 1, 1 in this angle brackets. It is ordered pair. We can form it. Now we take another constant, which is minus. Minus is a set, is a subset in R by R by R. Yes, so it is some element of our superstructure. So it is one element. We take restriction on other element. It makes sense in this case, and all this is equal to 0, which is also a constant. Yeah. So this is a perfect formula. No, in this case, this formula is correct. And this formula contains no variables. Yes? This formula contains one variable. So this formula, let me write this gamma equal gamma depending on x. Yes, so x is a parameter of this formula. Yeah? Now, if you write this formula, in this formula, here you have in this part of in this part you have this variable x, but here it is preceded by this quantifier. Yes? And in this case, this x is eliminated as a parameter or argument of this formula, because in place of this x, we can substitute any element of our universe. Yes? Not true, but no specific x is here. Yes? And now here you can substitute any element of x, but here we have some other statement. So in this formula, in fact, says something which does not depend on x. It is true or false, but not does not depend on x. So in this formula, this x is eliminated, like say variable x or t in the integral. Yes, after we apply the integral, then this variable is eliminated. The result doesn't depend on this specific variable. So this formula beta has no parameter. Or no free variables. And so if you have a formula which contains this quantifier there exists, then each such quantifier binds one variable. Yeah? No, after we apply this quantifier, we have to replace all, take all the entrances of this variable, and we have to be sure that we are talking about one and the same variable. Yeah? And then we cannot use this variable in any other sense. So if, say, we have there exists x, and then somewhere far we write x, say, equals something, we cannot do it because x is already eliminated by this quantifier. Yes? So in this case, it is already bound. So if we have some variables which are not bound, which remain free, yes, then after we look at the whole formula, then it's fine. So in general, a formula, say alpha, has some number of free variables. Say x1 and so on, xn, no, for some n. Yeah? And so we write x1, x2, xn. These are free variables. Now we can take this formula and replace x1 by some concrete name of some element, x2 by some name, and so on. We will, if we replace in the formula alpha all instances of x1 by, say, b1, all instances of x2 by b2, and so on, where the I elements of our structure, yeah? We get a formula alpha of b1, b2, so on, bn, having no free variables. So we have two ways how to bind the variables. Either we write them after the sign, after the quantifier exists, or we simply assign them some particular value. The value of them is some element of our superstructure, so it can be element, set of sets, and so on, depending on where we are. And now the definition. a formula without free variables is called a statement. A formula first. Of the form alpha of x1 xn having three variables x1 xn is called predicate. No, let us consider examples of statement and predicate. Example of statement. There exists x, say A in R, there exists B in R. It should be, these are the names. Now I go further, such that A times A plus B times B equal, say, 100. Okay, 101. Let me put it in brackets. So this is continuation of this formula. So the formula is formally a string, but it can be long, so we can write it, in fact, in several strings. So there exists, no, in our mathematical language, a square plus b square equal 101. No, for example, a equal 10 and b equal 1, it's enough. Yes, I don't care if it is true or it is not true. It is grammatically correct. And grammatically, it says that here we have two variables. Let me write, it is variable. So it is x, it is y, and it is n. To be consistent, x dot x plus y dot y equals 101. So this is a statement. It is something which can be true or it can be false. Yeah. It is a statement. What is a predicate? Predicate. Just a minute. This is a statement. Predicate is the following. Alpha of x is the following following formula. X element of n there exists y in N such that y plus y equal x. Please, who says what does it mean? What is the meaning of this? So this depends on x. Yeah. So what is written in the right hand side, please?
The even numbers.
Yeah.
That's what.
What is the written here? Okay, let's go. X element of N. So X is a positive integer. Yeah? So, first of all. And second, there exists Y, also positive integer, such that Y plus Y equal X. So what does it mean? What is the property of X?
It's whether it's even or...
Huh?
If it's true if and only if it's even.
This says that X is even. Simply so. The first says that X is integer, and second that X is even. Yeah? So alpha of X is the same. Now this is, say, logically the same as that X is even. Integer and even. Yeah. So if you substitute here something different from integer positive numbers, say the set of points of a square, yes, then the first will fail. So it will be false, so everything will be false. Yeah. So we can. It is not to say that we cannot say that is the square even and odd or odd. We simply said it is not true that the square is an even number. Square is not number, and so it is not an even number. Yeah? So in this language, now let me go to the say semantics of this. So if you have a term, we have to define the meaning of this term. Yes? Suppose we have a term which contains no variables. So, closed term. No. So first consider this. Suppose that you have mu equal some element, some constant. It is the name of some element of our universe. So B is the name of some B in our universe. Yes? So we have always to distinguish between things and their names. Yeah? If mu is b, then you say the meaning of mu, it is written like absolute value, equals just b. So if you say the name of some object, then the meaning of this is object itself. Similarly, the meaning of, say, mu, if mu and nu have no parameters or no variables, it is simply by definition, it is the pair meaning of mu, meaning of mu. Because the ordered pairs are defined for elements, for the things, not for the words, but for the things. Yeah? The meaning of, say, mu restricted to nu equals meaning of mu restricted to meaning of mu. Now, suppose we have a term dependent which contains some parameters. x1, xn. A term containing parameters x1, xn. So we cannot attach a meaning to this term as it is. Yeah? But if you substitute some constants in place of variables, then you will have a closed term which contains no parameters. Also, we substitute parameters or variables by constants. Yeah? So mu of b1 bn is a closed term and has a meaning for any bi, the names of bi in S. Yeah? So, no, for some bi it is well defined, for some other it is not well defined or not defined at all. If it's not defined, it is empty set. Yeah, so it is always defined. So this way we give a meaning, so either it is absolute meaning or a meaning depending on the values of parameters. Very simple. Now the meaning of the formula. Suppose we have a formula alpha, a formula. It can contain or can contain no free parameters. Now we somehow attach to this alpha the meaning, but formula, unlike term, has the just two meanings. It is either true or false. Yeah. So we have to somehow define the value of this formula. The notation is alpha. So this is the meaning of the alpha. Yes. So this, what is written here, is read as alpha is true. So this statement can itself be true or false, of course. Yeah, and assumes two values: true or false. So this is a Boolean variable. Yeah, Boolean variable. Now, how to ascribe what is true and what is false? It is the most, the deepest question in all the knowledge of what is true or what is truth. Yeah. So here it is settled in this way. So mu and nu are terms. So when terms in this case without free variables. Let's start from the beginning. Then this is true if value of mu or meaning of mu equals value of mu. Yeah. So mu and nu themselves are just notations, just signs, symbols on the paper or on the blackboard, but their meanings are real things. Yeah? So one thing is you say $1 million, all right, and the other if you have $1 million really in your pocket. Now, mu is element of nu. True if the meaning of mu is element of meaning of mu. Now if you have two already two formulas. One moment. If mu and nu contain variables, x1, xn, no, say part of them can be in mu and part in nu, then the formula say mu equals nu contains say let's call alpha, which is these variables x1 xn and mu of x1 xn equals nu x1 xn depends on x1 xn. So this I would say truth value of this formula depends on parameters. So for each value, concrete values of x1 and so on, it can be either true or false. Yeah. Now let's go on with this. So you consider two elementary formulas. Alpha, beta, and so on formulas. And the truth value of negation of alpha, so not alpha, is opposite to the truth value of alpha. So if alpha is true, so if this is true, then this is not true, this is false. If it is false, this is true. Truth value of alpha and beta it is true equals t if truth value of alpha is t and true value of beta is t. If and only if. Yeah? And truth value of there exists x in some mu such that alpha is true. Alpha depending on x. It is true if and only if alpha of some c equal t for some c. No, so c is this. So here is C itself, element of our universe, and here the name of this. Yes. Now, if you have arbitrarily long formula, then it is built by recursion from these elementary pieces. Yes? Yes, please.
So if we have a formula with 3 variables,
Yeah?
its meaning is a function
Of
from-
this variable.
of this or those variables.
Yes. 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 No. For example, example of this formula, or relatively simple formula. There exists x in n. There exists y in n. There exists z in n, such that x to the power n plus y to the power n equal z to the power n, and n more or equal than 3. Yeah. Now here we have to define x to the power of n. How to define it? It is defined recursively. X to the power 1 equals x. X to the power n plus 1 equals x to the power n times x. For example, like this. So please tell me, what does it mean, what is written here? This is continuation of this. Maybe somebody else. There exists n also. N. We have to add there. So what does it mean?
There exists positive integers x, y, z, and n such that x to the power of n plus y to the power of n equals
No,
x to the power of n.
what's the name of this?
Oh, the sum addition, was it?
What?
The relation.
How it's called?
Operation? No, wasn't it?
No. Okay, it's called the Great Fermat Theory,
Oh,
which was proved some time ago. So this statement is true. Yes, please.
Wouldn't it be the negation of all this?
Negation of all this. So if you write this here,
Wouldn't that be the Fermat, the great Fermat theorem? Like the theorem says that there is no such integer.
I'm sorry. No, this formula, I did not say that the formula is true. Let me call this formula phi, yes, in honor of Fermat, yes, and then I say that the truth value of phi equals false. Yes? So here I say take this formal statement and somehow found its meaning. So meaning of the statement is a Boolean variable, true or false. So this concrete statement is false. Yeah. If you write here something like 3 times this, yes, then I am not sure. Yes. I think for every factor, integer factor here, it is a problem in itself, and certainly for some of them it is true. There exists solution. If I change the equation, but if I keep this equation, the initial of my equation, then it is, we know that this is false. Yes? But this example shows that it can be false, it can be demonstrated, but the demonstration can be tricky. Yeah? Instead of this, we can possibly write something which is equivalent to the Riemann hypothesis, for example, which is almost hopeless for now. Yes, so it is either true or false, and if there was some creature, infinite creature, which can check all the particular cases with infinite accuracy, then it would be able to find the answer, is the Riemann hypothesis true or false. But no, in principle, it has some meaning. Okay. Okay, now this language is capable to already somehow describe all existing mathematics. So we have the material base of this is our superstructure. We take the sets and different objects from the superstructure, and we have this language to form some interesting sets, which and to express some ideas about these sets. And this language is powerful enough. My God, I have only 1 minute left. Okay, it is powerful enough. So let me give you the last piece today. It is definition. What is definable set? Suppose we have set A, which element is element of our S. of our unifiers. A is called definable if there exists a formula alpha of x such that A equals A is the set of elements of our superstructure such that for these sets, this formula with parameter x, its value is true. So we can somehow define set we can somehow define the set A by some formula. Here all conditions are important. Here set A should be element of S. So suppose we have a formula is the formula x equals x. So the set of A in S, so all elements of our such that A equal A. So any element of S satisfies this. Any element is equal to itself. Yeah? So it is S. Yeah?
If I understood correctly, shouldn't there be like A with the little the date thing in bottom right?
Yeah.
Like alpha of A is, should the A be like the name of A and not A there? If I understand, I just want.
Yes, alpha of A, yes.
Okay. I just want to be sure.
Yes. So let me write A equal A. So what is wrong with this set? The set is the whole S, but the whole S is not element of S. Yes? So S consists of different flow, different levels. S cap is union of all these levels. So it does not belong to any particular level. It has elements of all levels. Yes? So this set is not element of S. Yeah? Any element of S is at some particular floor with finite number. Yeah? So we have to write correctly. Example prime alpha of x is the following. X element of some Si and x equals x. So in fact this depends on two parameters, x and I. So consider this formula. So first of all, they should be all at the level number I, which is somehow specified here. And second, they should be equal to themselves. Now all elements at the level number I are equal to themselves. So corresponding A equal say A in S such that alpha of X of A I correct alpha of A I is simply S number I. Because first it should be at the level Si, otherwise it is not true. No, Si includes all the previous levels, yeah? So it is false if it belongs to some Sj where j more than I. Then it fails. And this is identically true. Yeah? So this means that it is Si and nothing more. Yeah? And so we never write, I would say, never write existential, say, quantifier without specifying some level where we are, or instead of level, specifying some set which is at that level. So it should be element of some set. Now, for example, as number I for some I. Yes, if you write simply element of S cap, this is not good because it is too much. It is a danger that we get a set such it has elements from all levels. It's not an element of our system. So we have to keep some discipline here, otherwise we get into paradoxes and contradictions. So we have to finish today and continue on Wednesday.
That's a quick question.